Hello everyone, this is Professor Keen. We have been discussing William Gilbert's On the Magnet. This is from A Student's Guide Through the Great Physics Texts, Chapter 1. In the previous lecture, Gilbert was talking about if you take a magnet, whether it's a bar magnet or a spherical magnet, and you break it in half, what will happen? Will the separate parts retain the same orientation with respect to each other that they had when it was one magnet, or will they reorient themselves? And one of the main points that we brought out is if you have a bar magnet with one end being labeled north, the other end being labeled south, and you split it lengthwise into two parts, then what happens is when you separate them, there will be a tendency for the parts to flip around compared to each other so that the north poles are repelled from each other and the south poles are repelled from each other, so that the north and the south will tend to line up. So if you have a bar magnet with my fingertips being the north pole and my palms being the south pole, and you break it apart, this one will swing around so that this north pole is near this south pole and this north pole is near that south pole. I hope that was clear. So anyhow, what we're going to talk about now is page 9 in a student's guide, where Gilbert gets into what he calls his chapter 3. And he's asking the question of how is it that iron can acquire verticity or polarity from a lodestone. You may remember that in one of the previous discussions, we mentioned that if you take a terrella or a spherical lodestone and hang a magnetized piece of iron near it, it acts like a compass needle and it swings around in a way to orient itself along a magnetic meridian, that is in the north-south direction. But this raises the question, how is iron magnetized? So in this section, his chapter 3, he's going to address the question of how is it that we can take a piece of iron, maybe an iron nail or a small iron filing, and give it verticity or polarity, which allows it to react to a nearby magnet. The way he says you do this is by taking an unmagnetized piece of iron and bringing it near a magnetic object like a lodestone and stroking the iron with the lodestone. When you do that, the magnetic lodestone transfers some of its power, he says, to the formerly unmagnetized piece of iron, and that piece of iron now acquires verticity or magnetization. The important point that he makes here also is that if you were to take this piece of iron after having rubbed it with a lodestone and you were to weigh it, it would weigh just as much as it did before you rubbed it. Why is this important? Well, because there is no material that is transferred from the lodestone to the iron. There's no exchange of matter. And this fits into his view that there is not a material cause or matter being created or transferred that gives the iron its magnetism. Rather, it's the form of the terrella or the lodestone that is rubbing against the iron. The form is transferred to the iron and it acquires a magnetic property by virtue of getting the form of this magnet. Iron, by the way, can lose verticity as well. Once it has been magnetized by a lodestone, it can also lose its magnetization. How do you do this? He mentions this in this section, that you can demagnetize a piece of iron by heating it sufficiently. So if a blacksmith takes this iron that is magnetic and holds it in the fire until it is red hot, eventually, and then brings it out and cools it down, it will have lost its magnetization. So this is one way to make it lose its magnetization. There are other ways as well. But he also says that once you heat this up and cool it down, if you cool it down in the vicinity of another magnet, as it's cooling, and then by the time it gets cold, it will still have a slight magnetization. So as it's cooling, if you reorient it now and then it will prevent it from acquiring the form of magnetism from any nearby magnets, or in fact from the magnetism of the Earth. Another point that he makes is the iron, when you're magnetizing it by rubbing a lodestone against it, it seems to acquire its magnetism instantaneously, or at least so fast that he's unable to determine the speed. This is unlike how heat is transferred through iron. If you put the end of a piece of iron in a fire, it takes a few moments before the end that you're holding grows hot. But on the other hand, if you take a piece of iron and touch it to a lodestone, one end of it touched to a lodestone, the other end instantly acquires magnetic properties. So it seems like magnetism is transferred instantaneously as opposed to heat, which takes some time to be transmitted. One other thing that I should probably say is that iron is sometimes called a ferromagnet. Why is it called a ferromagnet? This actually has etymological reasons. So ferro is a Greek word meaning to carry or to bear. And so iron, once you magnetize it, it seems fairly robust. That is, it doesn't lose its magnetism very easily. It carries its magnetism around with it, unless, of course, you sufficiently heat it to destroy its magnetization. Okay, let's go on to William Gilbert's chapter 4 now. What I've just been discussing was from his chapter 3. Let's go on to chapter 4, which is from page 10 in a student's guide. I'm going to turn up my webcam and draw some things. All right, so this is chapter 4 of Gilbert's On Magnetism. And this is from chapter 1 still of A Student's Guide, volume 3. Okay, here's a question that we'd like to address in this chapter. Which way does an iron compass needle point if it is magnetized by a lodestone? Which way does an iron compass needle or iron needle point after having been magnetized by a lodestone or some other magnetic object? Okay, this, by the way, is on page 11. Okay, so how should we think about this? Well, we have to think about it in terms of the Earth. So let's draw a picture of the Earth. I know Gilbert usually draws a North Pole on the left, South Pole on the right. I'm going to go ahead and draw it in the way I'm more comfortable with, the North on the top and the South on the bottom. This is the Earth and the equator of the Earth. Okay, and let's suppose that you have a lodestone that you've mined from the Earth, and you want to identify the north and south ends of a lodestone. You'll see where I'm going with this in a moment. So what you could do is you could hang this lodestone. I know this is a very big lodestone in my drawing, but let's suppose you hang this lodestone from a string toward the Earth. So this is our lodestone. And it will orient itself so that the north pole of the lodestone will point toward the south pole of the Earth, and the south pole of the lodestone will point toward the north end of the Earth. So I'm going to color code. So all the north ends I'm going to color code red. So this is the north end of the Earth. So of course, whatever end points away from the north end, I'm going to put a red mark on that. So we're kind of calibrating our lodestone using the north pole of the Earth in order to do that. Okay. And now what we're going to do is, let's say we then take this lodestone into our laboratory. So this is the lodestone that we've just calibrated. We know which end is the north end of the lodestone. And now we take an unmagnetized piece. So this is our, once again, our lodestone. Now we take a piece of iron, a little iron needle. Okay. And we rub the lodestone against this. We touch this and we rub the end. And what Gilbert argues is that the end, if we rub the north end on it, this end will become a south end, and this end will become a north end. Okay, so let's put a red dot then on that end of the iron needle. So we're going to rub it. This is our iron needle that was formerly unmagnetized, but according to Gilbert, it has acquired the form of this lodestone. It is now a magnetic object. And now what we do, and this is the question that's being asked, if we hang this near the Earth, which way is it going to point? Well, let's draw the Earth once again. And the Earth again has north and south. And let's draw our red dots on it once again. And if we were to hang this iron needle, it would rotate again so that its north end points toward Earth's south end. Okay, so it would rotate like that. Okay, so this kind of provides a way of understanding the magnetization process, and then how the thing that has been magnified will orient itself when it's placed near the Earth. Okay, and one of the main points that Gilbert is making is that magnetized objects can infuse, he says, can infuse a magnetic form into other magnetizable objects. So the iron has the potential to be magnetized. You know, a piece of glass, it doesn't have the same potential to be magnetized, but iron has the potential to be magnetized, and a magnetic object can then act on it to magnetize the iron. Okay? And what he says on page 12 is that in all of these demonstrations, it is ever to be kept in mind that the poles of the stone, as of the iron, whether magnetized or not, are always in fact and in their nature opposite to the pole toward which they tend, and that they are thus named by us. Okay, so here, the way that this thing tends is the opposite. It's pointing away from that pole of the Earth. And this is something that he emphasizes.